Welcome to part 2 of this tutorial, Fairness Against Data Bias. I will first cover motivation and issues for fairness, and then introduce a couple of fairness measures. Fairness is a subjective term. Many measures have been proposed. Then I will cover unfairness mitigation techniques for solving unfairness. Finally, I will cover a technique called FairBatch selection in more depth. So to motivate fairness, COMPAS is a software tool that's used by US courts to predict the defendant's risk of committing another crime. This is a very convenient tool because it saves a lot of effort by the human judges. However, a recent report by ProPublica says that COMPAS tends to overestimate Black people's recidivism risk compared to white people, which is problematic. So why would this happen? Well, there could be multiple reasons. Reason one could be biased data. So training data can be biased where there is more data for certain demographics. Reason two could be external factors. The surrounding environment may have caused more crime rather than race. Yet another reason could be maybe we're just using the wrong fairness criteria. So the fairness measure for use for development may not accurately reflect reality. In general, fairness is an extremely complicated issue, and so we won't have time to cover everything. But in this tutorial, we will focus on fairness with technical solutions. So to illustrate how to measure fairness, this is a model, the simplest one that I can think of. It's a perceptron that receives the following input features, and it has the following weights. The features are whether a person is a Black person or a white person, and whether the person has previous crime. And it takes a weighted sum and compares the result with 0. If the result is at least 0, then let's say the model predicts recidivism. So let's go through this example. For this young lady, the race equals Black feature has a value of 0, race equals white is 1, and let's say this person did not commit previous crime. So then if we take the weighted sum, then we'll have a result of -1. So since -1 is less than 0, the model does not predict recidivism. And we can actually interpret this result. It's saying that this person is white but has no previous crime, so therefore probably no recidivism, which seems to make sense. Let's say that this person has the following features. It's a white person, but let's say the person committed a previous crime. So in this case, this feature becomes 1, and the weighted sum is now 0. Okay, so in this case, the model predicts recidivism, and the interpretation is that this person is white but has a previous crime, so likely to reoffend. Again, this sort of makes sense. Finally, let's consider this person who is Black and did not commit previous crime. Now, it seems like this person should, also not, probably, be predicted to not commit to recidivism, but the weighted sum is still at least 0. So what's going on here? Well, it turns out that the race equals Black feature has a large weight of 2. So by having this feature with a value of 1, the sum is still larger or equal to 0. So the interpretation is that although this person did not commit a previous crime, this person is Black, so is likely to reoffend. And this is obviously a wrong behavior, but I'm just using this as for illustration purposes, where to show how a model can actually discriminate. Okay, so using these 3 data points, now let's go through a few fairness measures. The first one I'd like to introduce is demographic parity proposed by Feldman. So here the objective is that sensitive groups must have the same positive prediction rates. More formally, we can express it as follows. So here, let's say that Z is the sensitive attribute and Y hat is the prediction. So Z equals 0, Z equals 1. Let's say this means like white person and black person. And why we want to compare the probability of y hat being 1. So that's the positive prediction rate. And we want to make sure that the two values are the same for the two different sensitive groups. So this fairness measure is simple, but it is used in several applications, including predicting crime, hiring, and giving loans. And if this is not, sophisticated enough, there are more complicated measures as well. So let's go to our running example and see if there's any unfairness going on according to demographic parity. So looking at the left-hand side, there are two people who are white, right? And among them, only one person has a prediction, positive prediction for recidivism. So therefore, the positive prediction rate is 50%, right? And on the right-hand side, we have this one black person. And here, the positive prediction rate is 100% because this person has a y hat of 1. So you can see that according to demographic parity, there is this result, there's unfairness going on. The second fairness measure I'd like to introduce is called Equalized Odds, proposed by Hart. This measure extends demographic parity as follows. It still wants to ensure that sensitive groups have the same positive prediction rates, but for two cases, when the label is 0 and when the label is 1. So the formulation is similar, except that we have this new condition, y equals a, where a could be either 0 or 1. The rest of the formulation is the same. Intuitively, equalized odds distinguishes qualified from unqualified people. In our running example, we need to now consider two cases where a equals 0 and a equals 1. So if a equals 0, we need to have the people that do not eventually commit crime. And let's say that these two people don't commit crime. So let's say y equals 0 for these two. In this case, the left-hand side is 0%, whereas the right-hand side is 100% because the prediction is 1 for this person. So for case 1, you can see that the model is unfair. Now for case 2, where a equals 1, on the left-hand side, we have one white person. Let's say that this person eventually commits crime. Since the prediction is 1, the positive prediction rate is 100%. On the right-hand side, well, we use the toy data set, so we don't have data points here, but we can easily see that for this model, if z equals 1, it's going to predict 1, right? So we can just say that the positive prediction rate is 100%. So in case 2, it looks like this model is fair. So notice that the results were slightly different than in demographic parity. And so equalized odds gives us like yet a new perspective of fairness. The third fairness measure I'd like to cover is predictive parity. And I'm going to explain why I'm covering these three measures in the next slide. Compared to equalized odds, the role of y and y hat are swapped. So here, we want the sensitive groups to have the same positive label rates when the prediction is 0 or 1. So in the formulation, you can see that compared to equalized odds, the y and y hat swapped positions, right? So why do we want to use this measure? Intuitively, this is useful when we want to ensure the model's precision rates to be similar for sensitive groups. Okay, so I'm not going to go through a running example again for this measure, but I think you get the sense of how to measure fairness. So the reason I covered the three measures is that it turns out most of the group fairness measures, like the ones I introduced, fall into the following three criteria: independence, separation, and sufficiency. These are defined in a fairness machine learning book written by Barokas. And I highly recommend looking at the book if you're interested in fairness. So independence says that y hat is independent of z, which is exactly demographic parity. Separation says that y hat is independent of z given y, which is exactly equalized odds. And sufficiency says that y is independent of z given y hat, which is predictive parity. And there are reasons for these names, but I refer to the details in the book. Interestingly, there is an impossibility result where no two criteria above can be fully satisfied together under mild conditions. And the proofs can be found in the book. Okay, so in addition to group fairness measures, I would also like to introduce two other important fairness criteria that is widely studied. So one is called individual fairness by Dwork. And here the intuition is that for two data points that are similar, their predictions must be similar as well. So more formally, the distance between whatever like f values of x and x prime must be less or equal to the distance between x and x prime. Okay, so in our example, if these two people are similar, then they must have similar predictions as well. The next fairness criteria I want to cover is called causal fairness. And here, the key characteristic is that it uses a so-called causal graph to analyze fairness. So in the previous measures, we were just looking at final results. But here, this is a more in-depth approach where we want to understand what's going on and see which attributes are affecting which other attributes. So it could be the case that race affects the zip code because it's known that people of similar races tend to live in similar places. That's what the data says. And depending on the zip code you live in, there's an environment around that in that zip code, which may affect the crime rates in that region. So that may be affecting the Compass software for making predictions. But there can also be some direct influence from race to Compass. So this is called unresolved discrimination. And the goal of causal fairness is to remove such edges. So I won't go into more depth on causal fairness, but you can refer to this paper and also the book written by Barokas I just mentioned. So I did a whirlwind tour of fairness measures. Now I'd like to cover unfairness mitigation techniques. So addressing data bias can be categorized into largely three approaches: pre-processing, in-processing, and post-processing approaches, depending on whether the bias is mitigated before, during, or after model training, as shown in this figure. So I will cover each of these approaches in more detail. So the pre-processing approach is to fix unfairness before model training. There are pros and cons. The pros are you can possibly solve the root cause of unfairness, assuming that unfairness comes from biased data. On the other hand, it may be tricky to ensure that the model fairness actually improves. So because you don't have access to the model training itself. So even if you do some fixes on the data, it's not clear if the model is going to benefit. Nevertheless, there has been a lot of recent research in this using this approach. And they can be categorized into three natural approaches. One is to repair whatever data you have. The other approach is to generate fair data from whatever data you have. And the third approach is to acquire new data from outside to make your training data fair. And I'm going to cover representative works that are highlighted as follows. I also like to explain what doesn't work. So, a naive approach to mitigating unfairness is to remove sensitive attributes. So at first glance, it seems like these, if sensitive attributes are the problem, why not just not use them? Well, the problem is these attributes are usually correlated with other attributes. So let's say that you want to remove these three sensitive attributes: race, gender, and income. The problem is, even if you remove them, you can utilize some other attributes to infer these values. For example, a zip code is known to be correlated with race because, again, as I mentioned, people with similar races tend to live in similar zip codes. Also, if you have a high credit score, it's an indicator that you might have more income. Finally, this is an interesting example. A browsing history could be used to infer gender. Because some sites are very popular among women, some other sites are popular among men. So if you go to that website, it's an indicator of your gender. So this doesn't work. And so I'm going to introduce the approaches that do work. The first approach is fair data repair. And I'm going to illustrate one technique by Feldman. The scenario is that we want demographic parity when admitting students by scores. So let's say that in this figure, the x-axis is a score like SAT score, and the y-axis is the number of students. And we have two distributions. One is for women, let's say the blue one, and another one for men, let's say the orange one. Now, if we use a single threshold like this dotted line to admit students, this will not satisfy demographic parity because we're going to end up admitting more female students than male students. So the solution is to repair this distribution by averaging the scores of the same percentile. So a woman that's top 10% is considered the same as a male student that's top 10% within the male population. So by doing that, we can come up with this unified distribution, and we can use this one threshold to admit the same male and female students with the same acceptance rate. Now, there are more details to this technique. It can be extended to support more sensitive groups, and also it can be extended to support partial repairing. So partial repairing is important when you also want to balance fairness and accuracy. So even if we obtain full, like perfect fairness here, this may not be the most accurate solution because we may not be admitting the smartest students anymore. So if you're worried about that trade-off, you use partial repairing, and details can be found in this paper. So the next approach I want to introduce is about fair data generation by Choi et al. So here, let's assume that we have a biased data set, which can be large, and a small unbiased data set that we can use for reference. Now, for step one of this approach, we train a classifier that distinguishes biased versus unbiased data. So in this example, let's say that biased data set has a lot of blue points, more than orange points, whereas unbiased data has similar numbers of these two colors. In that case, the classifier is going to say that blue is more likely to be in biased data. Okay. So we're going to use this classifier in this second step. So in the second step, we train a generative model like GAN, or generative adversarial network, using the expected loss on unbiased data. So that was a mouthful. So let me explain what I mean. A GAN usually has a structure like this figure, where you have real data coming from above, and you have a generator here that's producing fake data. That's also realistic. And both of these go to the discriminator, which tries to distinguish real versus fake data. So if the training is done properly, then the generator will be smart enough to generate realistic fake data, while the discriminator will be really good at telling apart real versus fake data. So that's the typical GAN structure. Now, on top of that, the novel contribution is to effectively unbias this data by reweighting the biased parts. In this example, giving smaller weights for the blue points here, and running this GAN. So as a result, the generator is going to produce unbiased synthetic fake data that's realistic. So now we can use the generator to generate arbitrary amounts of unbiased data. The third approach I want to introduce is fair data acquisition. So the idea is, well, the motivation is there are a lot of publicly available data sets around us, and also data set search engines. And so we can actually acquire data more easily than before. Now, simply acquiring lots of data is not always useful, especially from a fairness perspective. For example, let's say that we have the following regions or groups on the bottom left, where we have a lot of America data, but much less data for Europe, APAC, and so on. So instead of, if we acquire more America data, this will only further bias the data, which is undesirable. Instead, we would like to acquire data for these other groups. The model fairness measure used here is called equalized error rates, which means that we want the model to be performed equally among different groups. That's a practical measure used in, widely used in the industry. Now, the problem is we don't know for sure how much data we would like to acquire for different groups. Sometimes we may need more data than other groups to obtain the same model performance. Okay? So in order to determine the amounts of acquisition, the idea is to generate and manage so-called learning curves. So learning curves look something like this, bottom right, where the x-axis is the amount of training data, y-axis is the estimated model loss. And you can see that it's a example. APAC has a slower decrease in loss than Europe. So this means that maybe we may want to acquire more data for APAC than Europe. The technical challenges here are first, how to fit the learning curves, and second, efficiently, and second, how to use the learning curves even if they are unreliable. And so these two challenges are addressed in this paper. So now I'd like to move on to in-processing unfairness mitigation. This approach is to fix model training for fairness. The pros are you can directly optimize accuracy and fairness. The cons, you may have to make significant changes in the model training itself, which may not be feasible in many real applications. So there are largely three approaches here. One is to add fairness constraints directly, so where you optimize both accuracy and fairness for training. Another approach is adversarial training, where you leave the model as is, but you compete it with another model that tries to figure out the sensitive values in an adversarial fashion. So this will force your model to become more fairer. The third approach is adaptive reweighting, where the idea is to give different weights to the input example so that the model training effectively has fair, like an unbiased input of data. So for these three approaches, again, I'm going to introduce the representative works that are highlighted as follows. So for fairness constraints, I'm going to introduce a work by Zafar. So here, the goal is to maximize accuracy with fairness constraints for convex margin classifiers. A margin classifier is one that uses a decision boundary and the distance from the decision boundary to data points, which is called to maximize the margin for training. Here, we want to satisfy demographic parity as much as possible. Okay. However, demographic parity itself cannot be expressed as a convex constraint. So this paper uses a proxy instead. The proxy is the covariance between sensitive attributes and the signed distance to the decision boundary. And I want to give an intuition why this works, why covariance is a good signal. So on the bottom, let's say that we're trying to classify circles versus squares. And let's say these colors, orange and blue, are the sensitive attribute values. Now, this is a good case where the covariance is 0. So you can see that the colors have really nothing to do with which side you are on the decision boundary, which means there's 0 covariance. On the right side, you see a bad case where most of the blue points are on this side of the decision boundary, which means that the covariance is either positive or negative. So by making the covariance 0, close to 0, you can ensure that the sensitive attribute is more independent of the prediction, which is exactly demographic parity. The The second approach I'd like to introduce is adversarial debiasing. So I'm going to explain a work proposed by Zhang. So the idea is to compete two models, a predictor that predicts Y, like recidivism, and an adversary discriminator that tries to glean the sensitive attribute information from these yeses or nos. And here, so this is trying to see if the person is black or white. Now, if this training is done properly, then you will end up with a predictor that's, again, really good at hiding the sensitive information and an adversary that's really good at distinguishing the race. And that's exactly satisfying demographic parity. And the paper also proposes other methods that supporting other fairness criteria as well. The third approach I'd like to introduce is adaptive sampling. So this is a type of adaptive reweighting proposed by Roh. So the idea is to adaptively select mini batch sizes to improve model fairness. So here, this paper is assuming that the model training uses stochastic gradient descent, which involves taking samples from the training data and training on these mini batches. Now, the problem is if you're not careful and the training data is biased, then simply taking a random sample is not going to be good for fairness because your sample is also going to be biased. And so if you don't do anything, the model is going to be unfair. However, so the idea of this work called FairBatch is to look at the intermediate model performance, and if a certain group is discriminated, increase its portion in the sample in the next mini batch. So here you can see that there are more blue points in the next mini batch. And so the technical challenge is how to determine these ratios. And so I'm going to cover FairBatch in more depth later on. So so for now, just assume that these sampling based approaches are another way to perform in-processing unfairness mitigation. So the final approach for unfairness mitigation is post-processing, where we would like to fix model predictions for fairness. The pros are, this may be the only option. This is the only option if the data and model cannot be modified. This could be because maybe you don't own the application or you cannot modify anything due to legal reasons. On the other hand, post-processing usually results in a worse accuracy because you are adjusting the final model. So among the post-processing approaches, I like to introduce a representative work by Hart. So I'm going to introduce one of the techniques in that paper. Let's say that we have a binary classifier M, and for each M, we can conceptually split it into two models, one for z equals 0, one for z equals 1. And that's for convenience. Later on, we're going to just combine the two models into a single model again. But let's say we have like one for each z. We then generate the following trivial models: a model that always returns 0, model that only returns 1, and an inverted model which always returns 1 minus the prediction of m. So pictorially, let me first explain the x and y axes here. The x-axis is the positive prediction rate for a certain z value when y equals 0. And the y-axis is the positive prediction rate for a certain z when y equals 1, okay? Now let's consider m for z equals 0 first. It's gonna be some point in this area because it has some positive prediction rate for y equals 0 and y equals 1. So it can be any dot. Now we start from here. We also use the three trivial models I just said. This is the 0 model, this is the 1 model, this is the 1 minus m model. And the idea is to combine these models probabilistically so that we arrive at a model that has the desired positive prediction rate for y equals 0 and y equals 1. So we can choose like any point within this parallelogram to obtain a model that has the desired positive prediction rates. Now we can do the same thing for m z equals 1. So again, we have the second parallelogram. We can choose any point here. And the idea is to choose a point that's in the intersection of these two parallelograms, that is the gray area. And once we choose a point, we can come up with a z equals 0 model for that point, a z=1 model for that point. And you can see that the positive prediction rates for y=0 are the same for the different z=0 and z=1. And also the positive prediction rate for when y=1 is the same for z=0 and z=1. So notice that this definition is exactly equalized odds. So by choosing any point in this gray area, we can come up with a model that satisfies equalized odds. Okay, and there are actually infinite number of models we can come up with. So among them, which one do we choose? We choose the one that's closest to the top left because top left point has zero loss. This is a desirable point because this is where, if y=1, y hat is also 1. And if y=0, y hat is 0, right? So top left is good. So therefore, in this example, we can choose the red point, which is as the model we want. So that was a little dense, but hopefully this gives you a sense of how we can indeed use post-processing to come up with a model that satisfies fairness. So now I'd like to go into depth on one of the techniques I introduced, namely batch selection for model fairness. So the idea is to perform fair sampling during batch selection, as I mentioned. FairBatch can be categorized as an in-processing approach, but it actually does not modify the training algorithm. So it's actually much easier to deploy. And I'd like to mention that this work is from our group, and slide credits go to Yuji Roh. But we believe that this technique is one of the state-of-the-art works right now. So here's the motivation. So I'm going to go through this more quickly. Model training commonly employs batch selection to get mini batches from training data, and random sampling is often used to select mini batches. In this setting, it's not a good idea to just take use random sampling for mini batches because especially if the training data is biased, because the mini batches are going to stay biased. So instead, so this can lead to unfair model predictions, right? And so the solution of FairBatch is to adaptively select mini batch sizes for the purpose of improving fairness. And it does that by adjusting the sizes with respect to sensitive groups based on the fairness of intermediate models. So after iteration 1, if group 2 is discriminated, FairBatch is going to increase its portion in the next mini batch. Okay, so conceptually it's straightforward, but the challenge is finding the optimal ratio that results in the best fairness. So the key features of FairBatch are twofold. One, it adaptively selects mini batch sizes to improve fairness. Internally, it solves a bi-level optimization problem for fairness and accuracy. And another important contribution is that FairBatch can be employed with a single line change of code, which I'm going to explain later on. And it also has good performance results. So FairBatch obtains high accuracy and fairness within one model training, and it's 15 to 96 times faster than other fair training baselines. And finally, it gracefully merges with existing batch selection techniques that are designed for faster convergence. Okay, so you can get the best of both worlds. So I'd like to flash this slide that shows the bi-level optimization details. So there's an outer objective that optimizes fairness, where it tries to find the best lambda parameters that determine the ratios of sensitive groups within the mini batch. The inner objective optimizes accuracy by performing empirical risk minimization. And in our paper, we show that under mild conditions, this F function is quasi-convex, which means that there is a global optimal solution. And so we design a sign gradient-based optimization algorithm, which approximately finds the optimal point. The algorithm itself is simple in the sense that you just adjust the lambda values depending on the sign, depending on which sensitive group is being discriminated. Now, the interesting part of this work is, despite the simplicity of the algorithm, there's an underlying theory that justifies why this approach works well. And so the details can be found in the paper. Now I'd like to emphasize the usability of FairBatch. So this is a typical sample code for model training. Now, if you take a pre-processing approach of fixing training data or in-processing approach of fixing where you fix the training algorithm, this is a lot of work, right? So it requires non-trivial changes either in the data generation or algorithmic design, both of which may be infeasible in practice. In comparison, FairBatch only requires the replacement of the sampler with this one-liner. Okay, so this can also be deployed in any existing machine learning pipeline. I'd like to show some experimental results of FairBatch. So FairBatch achieves fair, accurate, and efficient results efficiently. So here I'm comparing FairBatch with pre-processing, in-processing baselines. We use two real data sets, COMPAS and adult census, and here accuracy, higher is better, unfairness, lower is better, epochs, lower is better. So we align the accuracy values as much as possible, so you just need to compare the unfairness and epoch results. You can see that for the results, baselines that have low unfairness, they have much higher number, they use many more epochs than our approach. So you can see that our approach is the only one that's accurate, fair, and also efficient. And you can try out FairBatch using our demo by clicking this link to a collab. So the FairBatch notebook demonstrates how fair sampling improves model fairness. It consists of three parts. One is the data downloading. The second is the generation of biased data. The third is comparing FairBatch with another non-fair baseline using three fairness measures. In summary, I covered various fairness measures and an impossibility result. And also I introduced unfairness mitigation techniques, which can be categorized into pre, in, and post-processing approaches. And then I covered FairBatch in more depth, okay? So the next part 3 is going to be interesting, where Yuji is going to talk about how recently fairness and robustness techniques are starting to merge.